The precise definition of a limit, part 7. Now we're going to look at infinite limits. Infinity is weird, but usually these problems are slightly easier than the other ones. Let's look at the precise definition for the limit as x approaches a of f of x is equal to positive infinity. This definition isn't too different from the other precise definition of a limit. So let f be a function defined on some open interval that contains the number a, except possibly at a itself. Then the limit as x approaches a of f of x is equal to infinity if for every number m is greater than 0, there's a delta greater than 0, such that if 0 is less than the absolute value of x minus a is less than delta, then f of x is greater than m. And this is that key chunk that we'll need to be showing each time. What this looks like sort of graphically is if we have a function that approaches infinity as f of x approaches a, we want to show that no matter what we're finding for our delta band, we'll always be able to show that f of x will be greater than m. Now we have the precise definition for the limit as x approaches a of f of x is equal to negative infinity. This is very similar to the previous definition, but now we're looking for every number n is less than 0, there's a delta greater than 0, such that if 0 is less than the absolute value of x minus a is less than delta, then f of x is less than n. So graphically, if we have some sort of function that approaches negative infinity as x approaches a, then we can always find some sort of band, I should have drawn this a little bit better, such that we have an n where f of x will be less than n. So we're trying to find out how close to negative 9 we have to take x so that this inequality here is satisfied. So since we're trying to take x to be close to negative 9, that means this negative 9 is that x value that we're approaching, so a. In order to try to figure out what this delta has to be, we need to remember that we're trying to show that if 0 is less than the absolute value of x minus a, so x minus negative 9, is less than delta, then f of x, which we can see is 1 over the quantity x plus 9 to the 6th power, is greater than m, which is 1 million. And just like before, we're trying to take this expression and transform it at least to the inside of that expression. Because as long as it's positive, we'll be okay. So let's see. First off, let's rewrite this 1 million. So we have 1 over x, the quantity x plus 9 to the 6th power, which is greater than, well, 1 million is the same as 10 to the 6th power. So then we can take the 6th root of each side. So we end up with 1 over x plus 9 is greater than 10. But we're trying to find an x plus 9, not a 1 over x plus 9. So we can take the reciprocal. So we have x plus 9 and 1 over 10. And you just have to remember that when you're taking the reciprocal with an inequality, you have to reverse the inequality symbol. So now we have our x plus 9 is less than something. So we're going to guess that delta is equal to 1 over 10. So we have to be within 1 over 10 away from negative 9 in order to guarantee that this 1 over x plus 9 to the 6th is greater than 1 million. We want to use the precise definition of an infinite limit to show that the limit as x approaches 0 of 1 over x squared is equal to infinity. So that means that if 0 is less than the absolute value of x minus a, so x minus 0 is less than delta, then then f of x, so 1 over x squared, is greater than m. And we need to find a value for delta. So let's simplify this. So this is the absolute value of x is less than delta. So we're trying to transform this 1 over x squared into just an x in order to figure out what we're less than on the other side. So there's a couple different ways to do this. I'm going to multiply both sides by x squared, since I know x squared is always positive. So I have 1 is greater than mx squared. Then I'll divide by m. So I have 1 over m is greater than x squared. And then I'll take the square root of both sides. So I have plus or minus the square root of 1 over m is greater than x. And since we're trying to have, well, I won't go there quite yet, so let's just reverse this real quick. So we have x is less than plus or minus the square root of 1 over m. And we're looking for just the positive, because delta has to be positive, so x is less than the positive square root of 1 over m. So x is less than 1 over the square root of m. And that is the delta that we need. So we will choose delta is equal to 1 over the square root of m. Now we want to use the precise definition of an infinite limit to show that the limit as x approaches 0 from the right of the natural log of x is equal to negative infinity. So let's draw a quick sketch of our graph real quick. So here we have a very quick natural log graph. And we're trying to show that as we approach 0 from the right, we have this n, and f of x will always be less than that n. So if 0 is less than the absolute value of x minus 0 is less than delta, then f of x, so the natural log of x, is less than n. So we're trying to get this natural log of x to look like, well, let's simplify this, so the absolute value of x, so that we can get a nice good guess for our delta. So we just need to solve this for x. So let's exponentiate that. So we have e to the natural log of x is less than e to the n. Since e and natural log are inverse operations, we have that x is less than e to the n. So we have that x that we were trying to get. So that means that we will choose delta is equal to e to the n. Now this is actually not an infinite limit, but we want to find the largest number delta such that if the absolute value of x minus 2 is less than delta, then the absolute value of 5x minus 10 is less than epsilon, where epsilon is equal to 0.1. So we're trying to show if this is true, then this is true, specifically for that epsilon equals 0.1, so I'll rewrite that real quick. So if the absolute value of x minus 2 is less than delta, then the absolute value of 5x minus 10 is less than epsilon, where epsilon is equal to 0.1. So we're trying to manipulate this so that it looks like the absolute value of x minus 2, so that we can figure out a good number for delta. So 5x and negative 10 have a common factor of 5, so we can factor out that 5. So we have the absolute value of 5 times the quantity x times the absolute value of x minus 2 is less than 0.1. So we have 5 times the absolute value of x minus 2 is less than 0.1. And we want to divide both sides by 5, or we can also think of this as multiplying both sides by 1/5. And since that 0.1 is the same as 1/10, we can rewrite that as well. So now we have the absolute value of x minus 2 is less than 1/10 times 1/5, which is 1/50. So we've found our absolute value of x minus 2. So that means that on the right of that inequality symbol, we should have a good guess for delta. So the largest number, delta, would be 1/50. Given that the limit as x approaches 0 from the right of 1 over the square root of x is equal to infinity, find values of delta that correspond to m is equal to 100. So that means that if 0 is less than the absolute value of x minus a, so x minus 0 is less than delta, then f of x, so 1 over the square root of x, is greater than m, which is 100. So we need to take this and transform it into, well, let's simplify this. So transform it into x so that we can get our delta. So I'd probably multiply both sides by the square root of x. So I have 1 is greater than 100 times the square root of x. And then divide both sides by 100. So I have 1 over 100 is greater than the square root of x. I could then square both sides of this. So I have 1 over 10,000 is greater than x, which is the same as x is less than 1 over 10,000. So now we have our x, and we have a delta value that will correspond to this m is greater than 100. So we have delta. That's a weird looking delta. That's also weird, but it's better. So delta is equal to 1 over 10,000.